What we'd like to do here is just talk about the different kinds of symmetry you will see in math classes after this. There are lots of symmetries in geometry, there are lots of symmetries in linear algebra, but this is a pre-calculus class, so what I want to do is only talk about the symmetries that you would see in a calculus class, or maybe physics or chemistry. First off, what in the world is a symmetry? This is in the notes. Not much else is, but I think this much is. A symmetry. When someone talks about a symmetry, they're talking about doing something to the plane so that part of the plane doesn't change at all. The word actually comes from sim, which means the same, and metry, which means measurement. What I would like to do is just look real briefly at the most symmetric thing we can probably see in algebra or calculus or physics, and that's just the unit circle, like that. Now, for example, if I rotate the whole plane, if it's a real circle, it never changes. And so that's going to be symmetric to every possible rotation of the plane. There are a couple of things that we've been doing. We've been flipping graphs upside down. You can see here that if I flip this graph upside down by taking the top and putting it on the bottom and folding the bottom on the top, it doesn't change. So it's got that symmetry. And it's also symmetric with respect to flipping from side to side. If I flip the right side over to the left and the left over to the right, it doesn't change at all. So it has all those symmetries. But it has lots of symmetries that we don't care about. There are two specific kinds that we care about in the math classes and the physics classes that come after this one. One of them is just called symmetry. Symmetry, and you're going to see these letters a lot, with respect to. So WRT means with respect to the y-axis. Like that. Now, what do we mean by that? Well, we have seen, for example, graphs where we flip the right-hand side over in the left and vice versa. But if I have a graph that looks sort of like this, if you've had some trig, and you're supposed to have had some trig at this point, that's cosine. Now you're going to notice that if you take the right-hand side and fold it over on the left, and take the left-hand side and fold it over on the right, you get the same graph. That's exactly what we mean by symmetric with respect to the y-axis. Now there is an algebraic thing you can do for this, and you're going to see this kind of notation in a trig class too, but we're going to do too much here. The idea is if f of x is on the graph and you fold over, you're going to get to the point to minus x, f of x. Actually, let's do it this way. Let's say f of minus x. Now, if it's symmetric with respect to the y-axis, the height of this point is going to be the same as the height of this point. The height of the point on the left-hand side is just f of minus x. The height of the point on the right-hand side is just f of x. And so this is usually what they tell you to look for when something's symmetric with respect to the y-axis. Because all this says is, if you try to plug in the point on the other side, you should get the exact same y value. Now, a quick check for some things that are symmetric with respect to the y-axis, and maybe one that's not. The most common one that is nice and easy. Let's just look at x squared. Graphically, that's just a parabola, vertex at the origin. That is symmetric with respect to the y-axis. We're good. But now let's do the check. Now for check, what we want is we want the left-hand side equal to the right-hand side. Now the right-hand side for this function is just x squared, so there's nothing there to do. The left-hand side says, look at your function. Wherever you have a minus x, wherever you have an x, put a minus x. So I'm going to take this minus x, I'm going to put it in here. Notice, by the way, it's the minus x that's getting squared. Now this is minus x times minus x, that's just x squared. So when I plugged in minus x, I got x squared. When I plugged in f of x, I got x squared. That tells me that it's symmetric with respect to the y-axis. Let's look at an example of one that's not. And you're going to notice, by the way, that the power changes. So this is just example 2. Let's look at f of x equals x cubed. We know what this looks like from algebra. It just looks like, you always call this an S curve. It never looks like an S to me, but it does look like that. you can see that it's not symmetric with respect to the y-axis. If I fold this over, I'm getting a very different graph. That should mean that the check shouldn't work. So what does the check say? The check says plug in minus x for x and compare that to your original function. If you get the same answer, it's symmetric with respect to the y-axis. Now f of x here, there's nothing to do, that's just x cubed. F of minus x, okay, what does that tell me to do? It says take a minus x and put it in for an x. So I'm going to get minus x quantity cubed. Now here, this is minus x times minus x times minus x. Two of the minuses cancel each other, but there's still one left over. And so what I'm going to get is minus x cubed. These are not equal, which means it's not symmetric with respect to the y-axis. So that's symmetry with respect to the y-axis. Graphically, it's real easy. You fold it over. Algebraically, it's easy to check. You just plug in minus x for x. If you get the same answer, it's symmetric with respect to the y-axis. If you don't get the same answer, it's not symmetric with respect to the y-axis. One final thing before we go on to our next symmetry. Why would anyone in calculus care if something's symmetric with respect to the y-axis? Well, let me just draw again our nice little thing. How about if we have something that goes like this? All right. Now, one thing you're going to find out in calculus, and Newton was the one who actually did this, that areas under graphs are really, really important. And so they're constantly calculating areas under graphs. If something's symmetric with respect to the y-axis, this area is going to be equal to this area, which means to calculate the whole area, I only have to do half the work. I just calculate this area and then multiply by 2. So if it's symmetric with respect to the y-axis, it's going to be half the work to calculate the area under the graph. That will be a big deal. All right, that's example number 1. Example number 2 is going to be something we really don't use much. Symmetry with respect to the x-axis. Now, why don't we use symmetry with respect to the x-axis? Well, let me just draw something. Any graph at all, doesn't matter. If this is symmetric with respect to the x-axis, that means you fold it over and bring it down here. You're going to get some weird kind of, humping over here like this. Now, the thing about it is, if it's symmetric with respect to the x-axis, this part and this part both have to be here. But if that's true, it's not a function, right? Every time you draw a vertical line, you're going to hit the graph twice, right? You're like, oh. Okay, so in calculus and physics and chemistry, if you're dealing with functions, you're never going to see symmetry with respect to the x-axis. We just don't use it. Now, finally, another one that's going to be very important is not symmetry with respect to the x-axis. It's going to be called symmetry with respect to the origin. Now what I'm going to do is draw a graph that is symmetric with respect to the origin. It's our S-curve. We'll try to describe what's going on there. I think I actually have to have it go up steeper like this. Now to be symmetric with respect to the origin, no one really thinks of it this way, but it really, really helps when we're doing something. What they want to be able to do is if you draw a line through the point and the origin and hit the other side, if this is x, f of x, this is going to be, can I see this? Can I see it down here? Maybe. This is going to be minus x, f of minus x. Now, if it's symmetric with respect to the origin, what we want is the height of this dot, which is negative, to be exactly the negative of the height of this dot. So we want the height of the bottom dot, which is going to be negative, just to be the same as the height of the other dot, but made negative. Now, that's a nice little thing. Why do we care? Here's why we care. Ready? And we'll talk about this in terms of calculus before we do something with this. If it's symmetric with respect to the origin, and you turn it upside down, you get the same exact graph. Because the same exact graph. So that's actually the symmetry that we're worried about, is that if you rotate it 180 degrees, do you get the same exact graph back? Now, before we start doing just a check with this, what do we want here? We want to know why in the world that anyone would care in a calculus class. Well, let's just get rid of some of this stuff. Like I say, people in calculus, for really good reasons, are fixated on areas. And the idea here is if I look at this area here and this area here, if it's symmetric with respect to the x-axis, I'm sorry, with respect to the origin, those two areas are going to be exactly equal. Now that's not the same thing as symmetric with respect to the y-axis, because what happens in calculus is that this is going to have a positive value, this is going to have a negative value, and when you add them up, they're going to wind up being 0. So that again means a lot less work, even more work, even more less work than symmetric with respect to the y-axis, because those two things will just cancel and you won't have to worry about them at all. Now, finally, remember what we just wrote down here, and then we'll check it for 2 examples, just one. What we had was we wanted that when we plugged in minus x for x, we got the exact same height of a dot made negative. So we're just saying the height of this dot is exactly the negative of the height of this dot. There are lots of things like parabolas where that's clearly not true. Let's look at an example. Looking at an example. Let's look at the example we did before. Let's make it a little bit fancier. Let's say, how about something like f of x equals x cubed plus 2x. I don't know what the graph looks like, but I do want to see if it's symmetric with respect to the origin. And so what we're supposed to check, see if I can get this all down here. We're supposed to check, so I'm going to write down is, although I'll often just put a question mark, is f of minus x equal, question mark, to minus f of x. Now again, one side's easy. The right-hand side just says take your formula and multiply by a negative sign, right? So what we're going to get here is negative x cubed minus 2x. The left-hand side is harder. It says wherever there's an x in our formula, put a minus x. So this is going to be minus x quantity cubed plus 2 times minus x. Doesn't look like the left-hand side is equal to the right-hand side, but there's more, right? This is minus x times minus x times minus x. 2 of the minuses cancel with each other, leaving a minus. So this part right here is just minus x cubed. That minus can come out, and I get like this. So that's actually f of minus x. Here was minus f of x, and you can see they're equal. Now what does that tell us, by the way? That says when you turn this graph around 180 degrees, or just think about turning the graph upside down, that's not flipping, you're rotating. You get exactly the same graph back, which is really pretty cool. One more thing. When the exponents are all odd, you're going to get symmetry with respect to the origin every single time. And because of that, they'll call functions that are symmetric with respect to the origin odd functions. I'm not fond of that. Symmetric with respect to the origin, I think, is better. If the exponents are all even, you get symmetry with respect to the y-axis. Again, I like the symmetry statement better. That's it for symmetries.